All right. So we are going to be taking a look at antiderivatives today. And then if we have enough time, we might move into 5.1 because 5.1 it's a very dense section. And I don't remember exactly which questions from these last sections we're putting on the final. So hopefully I'll know more next week, have a better idea. But antiderivatives are exactly what they sound like. So think about this. If we have the function 3x squared, and we're told that's the derivative, what would the original function be if that's its derivative? So think about how our power rule normally works. So normally I have like x squared, and then the derivative of x squared is we bring the power down, and then we go 2x to the first. So now we want to think about what happens if we do that backwards. Or if I think about, all right, if I ended up with 3x squared, what is the antiderivative of that? Yep, x cubed. So we're going to think about it in a general sense then. If I have x to the n, my derivative of x to the n is n times x to the n minus 1. So I brought the power down, so I'm multiplying by the power, and then I take one off the power. So now I want to undo those steps. So instead of taking one off the power, I'd add one to the power. And then instead of multiplying by n, I want to divide by n. But here's where doing a process backwards, the order you do it backwards in matters. So normally we bring the power down and then subtract 1. When we're doing the process backwards, we also have to reverse the order of the steps. So I add 1 first and then divide by what I just added, like that result. Yeah. So this is the antiderivative of the power rule. Now, the notation we use for an antiderivative is we say a function capital F is the antiderivative of little f if the derivative of capital F equals the original function. So we're going to have f of x is our like usually given function. f prime of x is the derivative, and then capital F of x is going to be the antiderivative. So that's the accepted like notation difference between them. All right. Now we have this weird thing about antiderivatives. So when I look at these two graphs, are the slopes at a particular point on these two graphs different? So the shape of the graphs looks the same. What's different between them, though? Say it again. Translated which way? Up or down from each other. So like this one has a y-intercept at -2. This one has a y-intercept at 5. But we can see at that point, like the slope is downward negative. Our maxes and our mins are all occurring at the same x values. So the difference between them is whether they're moved up or down from each other. But if I took the derivatives of both of these functions, their derivatives would be the same because the slopes are all the same at the same x values. And that difference, that translation between the two is just a number that's added onto the function. But when we take the derivative of that, that constant at the end becomes 0 and goes away in our derivative. So when we do antiderivatives, we have this, oh, was there a constant at the end that originally went away and now I'm having to put it back? So to take care of that arbitrary constant, we put a plus c on the end of our antiderivatives. So f of x with 0 as our constant or plus c, c could be any constant. All of them are an antiderivative of f. So the most general form of the antiderivative is going to be the capital F of x, but we're going to have to tack on this plus c because we don't know if our actual original antiderivative graph was translated up or down. All right, so here we got some practice. So we're going to do the antiderivative of each of these terms. And then at the end, we're going to remember our plus c. Now, these are all just polynomial terms, so I can apply my antiderivative power rule to each of these. So x squared, the antiderivative of that would be x to the third, and then I divide by that number I just got, 3. Now, it's still going to be multiplied by the 3/2, because we know in our derivatives, the constants we just write it in front and multiply by it. Constant multiplication just carries through. So it also carries through when we do antiderivatives. So we're still going to have this minus. Then x to the 12th will become x to the 13th over 13. Plus 10 times x to the 11th will now become x to the 12th over 12. And then at the end, we put a plus c. For that unknown arbitrary constant. Now we can clean this up just a little, just because there's a couple of spots where there's coefficients. So the 3 on top with the 3 on the bottom cancel out. So we have 1/2 x cubed, or we could write it x cubed over 2. Either's fine. Minus 1/13 x to the 13th plus, now the 10 and the 12 are both even, so they reduce. So that is 5/6 x to the 12th, and then plus c. I usually like to write the constants as fractions in front, just so that way I can kind of clearly see here's the coefficient of the term versus the term itself. But for web work doesn't care which way you type it. So questions so far about how antiderivatives work, why we're doing that plus c. Now, when you're first getting used to antiderivatives, especially if you're still like struggling to remember all the derivative rules, one of the things you can do is take the derivative of the antiderivative function you got and make sure that it equals the original step in the problem. So this would be 1/2 times 3x squared. That'd be 3/2 x squared minus 1/13 times 13x to the 12th. Those will cancel out and we'll just have minus x to the 12th. Plus 5/6 times 12x to the 11th. The 6 and the 12 cancel and become 2. 5 times 2 is the 10. 10x to the 11th. And then the derivative of the constant would be 0, which we don't have to write. So that is our antiderivative. All right, now this one's a little more interesting. So let's look at that function, think about what we can do with that. All right, so they've got this minus outside of some parentheses. And that is just like extra brain power that my brain don't want to deal with. So I'm going to treat that like a -1 and distribute across the addition. So I'm going to write that as -9 cosine of -11x, and then it'll be -9. So I haven't done any calculus. I was just doing some algebra cleanup. Now, one of the things I find, especially when I'm first like learning antiderivatives and even later on, if I'm not sure how the antiderivative is going to go, I'll take the derivative and see how that goes, and then think about what would it look like if I tried to undo this process. So this is our like side thought bubble. If I was going to do f prime of x, the -9 would multiply through, And then the derivative of cosine is negative sine. But then I don't have just cosine x, I have cosine negative 11x. So there's a chain rule that comes into play here. So I would multiply by negative 11 because that's the derivative of the inside. And then that minus 9 at the end would just be minus 0. So I've got to think about, how do I undo the chain rule that showed up in here? So now this particular chain rule, the derivative of the inside is just a constant. So I can like do this multiplying by the constant backwards by dividing by that constant. All right, so when I come over here to start doing capital F of x, the antiderivative, the negative 9 is just going to carry through. The antiderivative of cosine. So now we've got to remember like which way the derivatives go and which way the antiderivatives go. So let's kind of sidebar that as well. So when I'm looking at sine x versus cosine x and I'm thinking about their basic graphs, the tangent line at 0 has a positive slope. The cosine function at 0 is equal to a positive number. So the derivative of sine is cosine. So that means the antiderivative of cosine is sine. And then I know the derivative of cosine is negative sine. So there's another antiderivative step. Derivative of this would be negative cosine. And then finally, the derivative of negative cosine becomes negative negative sine, which is sine x. So that means the antiderivative of sine x is negative cosine x. So until, like, eventually I memorized this whole thing. But this is like the thought process I would go through before it became very ingrained in my head. And I would like, on my first tests in Cal 2, like I would write, like I'd write my sine and my cosine, and I'd write the arrow with the derivative. And then I'd write the up arrow for minus cosine with antiderivative. So just to remind myself, like, which way derivatives went versus antiderivatives went. And so that way I wasn't like struggling in my head to remember which way it went. I just had to do the like big thought once, write it down, and then I just used it as a quick cheat sheet reference. So when we're looking at cosine here, antiderivative of cosine, cosine goes back to sine. So this will be sine of negative 11x, because when we did the derivative, the inside of the trig function stayed the same. So when we do the antiderivative, the inside of the trig function will stay the same. But we do still have to account for that chain rule backwards process. So instead of multiplying by the negative 11, I'm going to divide by negative 11, which is the same as multiplying by 1 over negative 11. So that right there is our antiderivative of the negative 9 cosine. But we still got that minus 9 to deal with. So 9 has an invisible, like a constant term, has an invisible x to the 0 attached. When we did the chain rule, did we get negative 11x? Like when we were doing the derivative of negative 11x is negative 11x to the 0. So like x to the 0 is 1, so we don't have an x term in there. Or I mean, well, we've got an x to the 0 in there. No, that's a fair question. So when we're undoing a chain rule, we're having to think about what would the function before be that when I take its derivative, I'll get back to this. So if I take the derivative of this function, the chain rule will come into play and I'll multiply by negative 11. So I need the 1 over negative 11 to cancel that eventual negative 11 that I'd multiply by. So it'll get back to just negative 9 cosine negative 11x. So let's finish the antiderivative and then we'll do the derivative so you can see it like doing the cancellation the way it needs to. So the negative 9x to the 0, that x to the 0, I'm going to add 1 and divide by it. So it'll be x to the first over 1. And then as always, there's that potential for some unknown constant term. Now I'm going to do a little bit of cleanup and then we'll do the derivative and then the derivative will have a little bit of cleanup. So the negative 9 times 1 over negative 11 becomes a constant 9/11ths in front times the sine of negative 11x. And then we have minus 9x plus c. So now we're going to check it by doing our derivative. So the 9/11ths is a constant in front. So that's just going to carry through. So 9/11ths times derivative of sine is cosine of negative 11x times our chain rule is times negative 11. And then minus 9 times the derivative of x is just 1 plus 0. So now my 9/11ths times negative 11th, negative 11 becomes negative 9 cosine negative 11x minus 9. So if I had a negative 11x squared, then I'd suddenly have like an extra x's in there that I didn't want to have. It also, in the derivative, it would cause a product rule, which would like make a whole bigger mess. So we're not going to look at antiderivatives of product rules. We're going to leave that for Cal 2 because undoing a product rule is really weird. So we'll see chain rules, but in this class, the chain rules are going to be very basic like this, where it's just a constant. But they can be more complicated than that. If they are, though, the like parts that make it more complicated will be somewhere else in the problem. So like if it was like sine of x to the third, our chain rule would have a 3x squared that gets multiplied in there. So to do our antiderivative properly, we would see at least an x squared in the function that they were asking us to do the antiderivative of. But when we have those like extra weird chain rule setups, we do what's called U substitution. That's our process to handle, here's my weird inside. Do I have my derivative of the inside to be able to do the antiderivative properly? But yeah, antiderivatives are very weird because you've just barely gotten a good hold on derivatives and you've seen some applications, and now we're like, all right, take everything you learned to do it inside out and backwards. And it's kind of like imagining what would my shirt look like inside out and backwards. Like we know what that looks like because we've done it ourselves so much. But like when you haven't done it that much, it's harder to imagine how to do something inside out and backwards. So that's why like the first part of Cal 2 is really just a whole bunch of how do we do the antiderivative of this? Now this.
Are we going over practical applications of this, or is it just a concept that we're learning so far?
So we're looking at just the basics of like how to do basic antiderivatives. Then we're going to look at, so you know how we did the long definition of the derivative? And that is like where the idea of derivative came from, and then they discovered the shortcut rules. So this is actually like the preview of the shortcut version. Then we're going to look at the long version and then see that this horrible long thing that we made you do once is really just doing antiderivatives, but we call it the integral. So Cal 2 will focus more on like the first half of the course is like how to do integrals in, different weird setups. And then the follow-on to that, although they also kind of do it at the beginning, is some applications of integrals. And then they go really weird into sequences and series, which feels very left field, except it is actually useful for like computer science majors or anybody who's going to program with something that has a small fixed processing power. But mostly it's just well, we had to suffer through sequences and series, so you do too. And I wish I had a better logic for it, but that's really about the most logical reason I found for why we do it. I did find one application 20 years after I did it. But I'm a math and a math educator. Like I didn't take engineering courses. I barely took chemistry courses. So I never got to a high enough level course to really see the applications. So I know they exist. I just can't name them. Oh yeah, like physical chemistry, they spend the first like month and a half teaching you new math that mathematicians are like, what's that? Like they have no clue. It's the only course I regret not getting to take. All right, so now we got this bullshit. So our function that we're supposed to antiderivative is 11 times cosecant 12x, cotangent 12x, and then they put a plus 3x. So anytime we see trig functions, like repeated trig functions, especially when what's inside the trig function is the same, that should like immediately ring some bells of like, wait, this is one of the weird trig derivatives, like one of the other guys. That's what I think of the other four as. So when it's a pair of trig functions, that's not our tangent and cotangent. That's either secant or cosecant. Now this is all the c's, so it's got to be a cosecant. But our cosecant derivative also has a negative. So we're going to have to account for that negative when we're doing our antiderivative step. So like looking at the structure here, seeing the cosecant cotangent, it's looking like structurally the antiderivative of that is going to be some variation of cosecant of 12x. So over here on the sidebar, I just want to explicitly write like, this is what I'm thinking is going to be part of my antiderivative. So let me think through what the derivative of this is so I can see where the extra pieces need to be in there. So if I did the derivative of this, I'd get negative cosecant 12x, cotangent 12x. But then my chain rule would say times the derivative of the inside, which would be a 12. So what I like to do is when I'm thinking about what would my derivative of my potential antiderivative like look like, I want to see what structural things I have versus what structural things I'm missing. So I've got the cosecant and the cotangent part in there. And that's good because those are the pieces that I can't really like put in there if I'm missing them. But what I don't have is I need to account for that 12 and I need to account for that negative. Now, those are both constant multiples, so I can just like do multiplying by those things backwards. So the same way we did the times 1 over negative 11, that's what we're going to do in our antiderivative. All right, so my 11 is just a constant being multiplied, so I'm just going to carry that through 11 times. Now my antiderivative of the cosecant cotangent mess should be cosecant 12x, but I need to account for undoing multiplying by 12, so I need a divide by 12, which is the same as multiplying by 1/12. But I also need to make that negative. Now you can write the negative on top with the 1 if you prefer to write it that way. Like it doesn't matter where the negative goes. Negative 1 on top, negative 1 on the bottom, or negative 1 in front of the fraction are all the same. So that handled the weird trig part. Now we still got the plus 3x. So plus 3 times, that'll become x squared over 2. And then plus c. Now just a little bit of quick cleanup. So that'll be negative 11/12 cosecant 12x plus 3/2 x squared plus c. And then if we checked it, our derivative would end up being negative, which would cancel the negative in front. We'd get a times 12, which would cancel the divide by 12. The derivative of x squared would be 2x. So the 2's would cancel. So we'll just have the 3 times x, and derivative of the constant would be 0. So yeah, it looks like all the numbers will work back to what we originally had. Now, what we're kind of hand waving and inside out doing here is a u substitution. Like, yeah. All right. Now here's our symbol for antiderivative. It's called the indefinite integral. Ooh, fancy. So just like d dx was our like operational symbol for saying do the derivative, this swooshy, slanty, almost S looking thing is an integral. So if I write that swooshy, slanty thing in front of f of x, now I do technically need this little dx next to it, because that dx is actually telling me what I'm taking the antiderivative with respect to. Because eventually, if you're going to take Cal 3 is multivariable calculus. So you'll do antiderivatives with respect to x, and then you'll do antiderivatives with respect to y. But before you do the antiderivatives, you actually learn about doing derivatives with respect to the different variables. And we've kind of done that already. It's just they do it with functions where both of the variables are present, so it adds extra craziness. But that is literally the bullshit they do in engineering courses. Because let's face it, reality is not single variable. Reality is multivariable. There's always more than one thing going on that you can track as an input. So for now, this integral symbol just means do the antiderivative and put the plus c at the end. Now, properties of indefinite integrals that we've already been using because we know they work with derivatives nicely is if I'm doing the antiderivative of the sum or the difference of two functions, like I just do the antiderivative of each piece and then put the plus or the minus in between them. The same with the constant multiplication. Like we were already using these rules. This is just explicitly stating them. So things that play nicely with derivatives play nicely with antiderivatives. So sums, differences, and multiplying by a number, derivatives just moved inside and did that just fine. Products and quotients. Remember, there's a whole product rule, there's a whole quotient rule. So integrals do not play nicely with products and quotients the same way derivatives do not play nicely with them. So we're not going to see products of actual functions, and we don't even do an antiderivative of the quotient rule. We turn it into a bullshit version of the product rule because there's too many moving parts in the quotient rule. So now we've just got practice with the symbol. But we're also doing practice with a, hey, here's that derivative that you kind of remember exists, but not what it equaled. So we wrote it off to the side here because we would not expect you to remember this antiderivative off the top of your head. That's too much memorization. Not saying y'all couldn't do it, just keeping the details correct between all of them is a pain in the butt. So my 1 over the square root of 1 minus x squared, that is the derivative of the arc sine of x. So that means the antiderivative of 1 over the square root of 1 minus x squared dx would be arc sine of x, and then, of course, with the plus c. All right, so first thing I'm going to do is I'm going to take that minus and that 12, and I'm going to move them outside the integral. So that'll leave me with a 1 on top as a placeholder. So moving out constant multiples, always fair game. Now, this 1 over square root of 1 minus x squared like literally matches our arc sine of x. And then anytime we do an integral, we always tack on that plus c. When I was first learning antiderivatives integrals, I always thought of the dx like turns into a plus c. That's not what actually happens, but that's just something my brain grabbed a hold of to remember to write the plus c. Now remember, arc sine is just a weird way of writing inverse sine of x. I don't know if we actually even put like one of the inverse trig functions in WebWork, but they might want you to type like sine -1, sine to the -1 of x for the notation. Whatever they want, though, they should have a note that tells you what they want. All right, now this one's weird. So 11 divided by x plus 2 squared. So looking at that, that's a quotient. And I said earlier, we don't do quotients. So the first thing is rewriting this so it's no longer a quotient. So that x plus 2 squared, to move it out of the denominator, I'm going to change the sign of the exponent. Now my 11 there that I multiplied by, that is a constant, so I'm just going to real quick move it outside the integral as well. So I've got 11 times the integral of x plus 2 to the -2. Now this is where I kind of sidebar. If I was doing the derivative of this, Well, my derivative here, this is setting up a chain rule. So I've got thing to the -2, so I'm going to use my power rule on that, and then I'll multiply by the derivative of the inside. So my derivative would be -2 x plus 2 to the -3, and then times the derivative of x plus 2 is just 1. So this is really just a power rule. It's just what's inside the power rule looks a little sillier. But other than that, I'm just using my power rule. So I'm going to use my antiderivative power rule. So we still have the 11. Oops. Now we're doing the antiderivative, so I don't write the integral symbol anymore. So I'll have x plus 2 to the -2 plus 1 divided by -2 plus 1. So when the numbers get weird, I will actually like write the plus 1 over thing plus 1. Now I do need to account for that chain rule. Now the chain rule is multiplying by 1, so I need to divide by 1. So it's not actually doing anything here, but if that inside was like 3x plus 2, then I'd be writing 1 over 3. It would make a difference. And then, of course, our plus c. So just cleaning it up a little bit, that'll be -2 plus 1 is -1. So this becomes -11 times x plus 2 to the -1 plus c. And if I took the derivative of this, -11 times, power comes down, -1, x plus 2 to the -2 times the derivative of the inside 1. And we get 11 times x plus 2 to the -2. All right, now this next idea is, well, if I knew my function, my thing was 4x cubed, and I wanted to know, like, f prime of x is 4x cubed. I wanted to know exactly what f of x is. So when I do my antiderivative, I get that plus c. So this is really asking, is there a way to figure out what the c value is? So that's where our follow-up, what if we also knew a point on the graph? So f of 0 equals 5. That means when my x value is 0, the function equals 5. And a lot of times, especially when it's 0, that 5 like ends up being our c value. We would still actually calculate it by plugging into the function because it's not always going to be 5. But that is how we handle figuring out the plus c value. And it's from knowing initial conditions. So we call this an initial value problem, which this is in a very basic sense. This is like the introduction to differential equations. So an initial value problem is a problem where we're given the derivative of the function and an initial condition about the function, and we're asked to figure out the original function. So we'll take the general antiderivative and we'll have the plus c. Then we plug in the x and y values and solve for the c value. So we're going to see that in action. So our derivative here is very basic. dy over dx equals negative 24x plus 7. And we're told y of 0 is 5. So first thing I'm going to do is I'm going to actually take this equation and I'm going to multiply both sides by dx. And now I'm going to apply my antiderivative on both sides, my integral. So the antiderivative of the derivative of y is just y. But over here on the other side, I've actually got a function to work with. So now we're going to do the antiderivative of this function. So the negative 24x, I'm going to keep my negative 24. And then the x will become x squared over 2 plus antiderivative of a constant is the constant times x. Because if I did the derivative of that, it'd go back to 7. And then my plus c. So I had a linear function. My antiderivative is a quadratic. That makes sense because the derivative of a quadratic goes down to a linear function. So now we've just got to use the initial value in our function to figure out what c is. So our y value is 5. Now my negative 24 divided by 2 is negative 12 times x squared. There's our first 0 plus 7 times 0 plus c. So we get a 0 plus a 0 plus c. So c is 5. So our actual final function is negative 12x squared plus 7x plus 5. So we did our antiderivative and we used what is typically an observable starting condition. That's why we call them initial values, because typically the values we get are what's occurring at time equals 0. Because when you do differential equations, you're using them typically to model a future event. So you don't know what's going to happen in the future, but you know where everything starts. All right. So now that we did that, we're going to kick it up a notch. So we've got a function ds dt equals negative 12t plus cosine t. So I'm just multiplying by the dt and then writing in my integral symbol on both sides. So this is now s equals, and now I'm going to do my antiderivative of each piece here. So we'll have negative 12 times t will become t squared over 2. I add 1 and then divide by that number, plus cosine. So sine's derivative is cosine, so going backwards, cosine's antiderivative is sine. And then, of course, our plus c. All right, so now we're going to plug in 0 and see what our constant comes out to be. So I'll have negative 3 for my s value equals, that'll become negative 6 times t squared plus sine of t, but I'm leaving blanks, plus c. We fill in zeros. So this is 0 plus sine of 0 is 0, because remember, sine starts at the origin. So input 0, get 0 out, plus c. So negative 3 equals c. So final result, s equals negative 6 t squared plus sine of t minus 3. Now, from what I remember of us discussing the final, I do think we put something like this, an initial value problem, on the final. So a basic antiderivative, but we also give you the initial condition so you can plug in and solve for c and give the actual function. Now, sometimes we get a little crazier. So solve the initial value problem, except they've given us the second derivative of the function and then 2 pieces of information, 2 points. They're not quite initial values because we're plugging in 1, not 0. But if you look at our second derivative here, if we plugged in 0, we'd get undefined. And that's probably going to carry through on our antiderivatives. So yeah. All right, so there's our second derivative. So I'm going to go back to my first derivative by doing the antiderivative. So I'll keep my 2 times t to the negative 2 plus 1 divided by negative 2 plus 1. And then I have plus c. So cleaning this up, that'll be negative 2 t to the negative 1 plus c. Now, before I continue on, they gave me one of my initial conditions is actually about the first derivative. So I'm going to use this point right now to figure out this c value. So when I plug in 1 to the derivative, I get negative 2 as my result. So I plugged in that initial condition and figured out that my constant is 0. So now I'm going to take my derivative, r prime of t equals -2 t to the -1, and then c is 0, so plus 0, so I don't have to write that. So I just have -2 t to the -1. All right, so now we're going to do the antiderivative. So I have -2 times t to the -1 plus 1. All right, -1 plus 1 is 0, but then I'm supposed to divide by -1 plus 1. And now we have a problem because we just wrote divide by 0. So I did this on purpose because if you're not paying attention, like your brain will just automatically like, oh yeah, power rule. This is the one instance where the power rule screws up, and this is what it looks like when it screws up. So if you're like, and I divided by 0, whoa, rewind. Okay, I can't use the power rule here. So I'm going to come back to our function, and instead of t to the -1, I'm going to write it as 1 over t. So do we remember what function has the derivative 1 over t? Yep, natural log. So when our power rule antiderivative fails, it's the natural log. So our like sidebar, remember, is the derivative of natural log of x is 1 over x. So the antiderivative of 1 over x is natural log x. So this antiderivative of 1 over t is natural log t. And then, of course, we get our plus c. Now, I did just write c twice. So if you want to call this d instead, or if you want to put subscripts on it so they're distinct, that's totally fine. And that's actually what you do in differential equations, just to differentiate between the two constants. But since our first one equaled 0, it's kind of like, whatever. So we've got that antiderivative like all the way back to our original function. Now we just need to use our other initial value, that r of 1 equals -2. So this will be -2 equals -2 times the natural log of 1 plus c. Now, natural log of 1, my brain always has to like step through hoops to remember what this is. So short answer is type it on the calculator. But this is saying e to what power equals 1. The only way to get 1 is if we get e to the 0 power. So the natural log of 1 is 0. So I have -2 equals c. So this means my actual function, r of t, is -2 natural log of t minus 2. So that is our very basic introduction to antiderivatives and initial values, which lets us solve for the arbitrary constant. So in general, you're going to see functions that match derivatives that you've been using a lot. They might be a tiny bit different with just a like baby chain rule inside, where the inside's derivative is a constant. So our summary slide, there is in the textbook a giant list of antiderivative rules, but they are literally just writing derivative rules backwards. So we can see in here on this third line, there's our derivative of natural log x is 1 over x. So the integral of 1 over x dx is natural log. We technically are supposed to write absolute value of x plus c, just because we're not supposed to take the natural log of a negative or of 0. But the 0 is already excluded because we started with 1 over x. So we can't put a 0 in there for x already. Now I want to take a look at the next section, which is approximating area under a curve. So we know there's a whole bunch of shapes we saw in geometry. Over and over again, we've learned these area formulas, cool. But what if we're dealing with a function and we want to know what's the area under the curve? So this starts like with the question, well, how could I find the area of that shape? Good question. I mean, I could guesstimate it by counting the squares, but that's real tedious. So what we do to take a look at that is we subdivide the region into equal widths. And then usually what we use to find these areas is a rectangle. But the question is, like, which height of the rectangle should I use? Should I use the left side? So I get those. Or should I use my right endpoints? And I get this whole thing. And it's hard to say which of those would be a more accurate representation of the area. But I can say, looking at my picture, like they're relatively close. Like it's not bad for a very rough estimate. But of course, we know in math, we can take rough estimates and do math magic and get better estimates. But before we do that, we're going to do area under a curve the long, tedious way. So we've got the function 1 over x. We want to approximate the area between the x-axis and the curve over the interval from 4 to 8. So if I take the heights of the rectangle by evaluating the left endpoints, so I need to first subdivide this into 3 rectangles. So my total length here, 8 minus 4, is 4 units, and I need to split that into 3 equal widths. Ugh, I can't draw lines. So like just looking at the picture, the tick marks are roughly there, but each of these widths is going to be 4/3. So that's just the distance between them. Now it said left endpoints. So I need to know my function value on the left here. Then I need to know my function value here. And then here. All right, so the base of each rectangle is that 4/3. So this is like B1, B2, B3. So my area formula is 4/3 times the first height plus 4/3 times the second height plus 4/3 times the third height. Now the heights are the function values. So like my first height is, I'm going to take 4 and plug it into the function. My next height, a little more annoying, but it's 4 plus 4/3. That would be the next x value. And then the next x value after that, which I need a little more room. My final left endpoint would be 4 plus 4/3 plus another 4/3, so 4 plus 8/3. Now I have my function formula. It's f of x equals 1/x. So I can actually evaluate my f values here. So I've got the 4/3, and then f of 4 is 1/4. Now let's see. 4 plus 4/3 is 12/3 plus 4/3, 16/3. So I have 1/16/3 plus 4/3 times 1/20/3. So annoying setup there, but we could actually like crunch, crunch. Actually, these aren't that bad. Almost. So I'd get 1/3. This would become 3/16. So we get plus 1/4. And this will become 3/20 plus 1/5. Now, based on our picture, I can also see that that area number is a little bit bigger than what the actual area under the curve is. So this actually gives me an upper bound for that area. If I did the right endpoints instead, it'd be a little smaller, and that'd give me a lower bound for the area. And then a common step after that is to average the two, which gives you kind of the midpoints. But this area under the curve is going to turn out to be what our antiderivative, our integral is. So Derivative finds slope of the tangent line. Antiderivative gives us a formula for area under the curve. So we're going to play around a little more with this. Hopefully by next week, I'll know how this will look on the test. Because I'm not sure exactly how we put a question from this section on there. But I think they said they did, so we'll see.